Namaskar my dear friends. Let us see a C2000 series microcontroller schematic design for 100 pin LQFP package. So if you want to use the automotive part, you have to use this part F280037 CPZ RQ1 or PZ RQ1. If you want to use non-automotive part, you can just replace with SPZ. Okay, so F280037 SPZ is non-automotive and with Q1 that is automotive part. But pin diagram is almost exactly same, so not a problem. Now what we'll do is we'll try to understand the same way what we have earlier done, like C2000 series microcontroller. This is my non-automotive part and this is my automotive part. Without C also there is one part that is available, which is going to be F280037 PZRQ1. Okay, so what are the things that we will see in this particular session is basically how we can connect a power supply connector, power supply management, and various other peripheral design. Okay, like ambient sensor, temperature sensor, humidity sensor, NTCs, all these things are there. That is going to be a part of this particular microcontroller. Okay, and this is going to be 100 pin LQFP that you have to understand. Okay, so this is very popular microcontroller that we are going to see, because this is going to be a part of all kinds of motor drivers, drone application, and your air conditioner, fridge, washing machines, or various other power tools and all. So everywhere this particular microcontroller is used to drive your motor controls. Okay. Good. So let us proceed that. So basically, first of all, what you have to do is you have to design this particular microcontroller symbol in such a fashion that you have, like, above you can see we have power supply pins, VDD pin, VDDIO pin, V reference pin, and VDDA, that is analog voltage pin, and we have internal regulator enable disable pin. Okay. Then we have downwards, we have ground pin, and we have V reference low pin and analog ground low pin. Okay. Then left side we have all GPIOs, arranged in such a fashion, like you can see GPIO 0 to 9, 10 to 19, 20 to 29, 30 to 34, like that. And right side also a few GPIOs are there, because I didn't have the space, so I put it right side as well. We have JTAG programming here, and then we have all the analog pin here. Okay, that ADC pins and DAC pins are here. Okay, understood? Now first of all, what we have to do is we have to do power supply. So power supply, basically the VDDIO is the main power supply for this particular microcontroller, which is going to be 3.3 volt. So this VDD is filtered and send it to VDDIO, and after this decoupling capacitors it is connected here. So all the 4 pins will be having each one of them one decoupling capacitor 0.1 microfarad plus 10 microfarad additional decoupling capacitor is there. Similar to that, VDD pin will be taking voltage from internally. So you can see here VRENZ is grounded. So from the datasheet recommendation, you can see if it is grounded, the VDD pin will be taking voltage internally, that is 1.2 volt from VDDIO. Okay, so this requires just external decoupling capacitor that is put here. So you can see we have put decoupling capacitor for each of the 4 pins here, 1, 2, 3, 4. Understood? If you want to give external voltage for this particular VDD pin, then what you can do is you can place this NC, you remove that and remove this one, so it will be pulled up, and then connect 1.2 volt here. Okay, externally. So 1.2 volt it needs, that you have to understand. Now next part that comes up is we are going to talk about programming of this particular microcontroller. So this C2000 series microcontroller actually supports JTAG programming. So this JTAG connector 10 pin, like a standard connector is there. So you can take this part as it is. Okay, and we have TMS, TCK, TDI, TDO, XRSN. Okay, the thing is, you can see here we have JTAG signals, and 2 signals like TDO and TDI can be used as general purpose signal also, but what we have done is we have dedicatedly put these pins for programming. We don't want to share this. Okay. Next comes up is microcontroller reset. So microcontroller reset switch is here. So if you press this, it will get grounded, like this VDD will be pulled down, and this is how this microcontroller will get reset. Okay. We have put external 12 megahertz crystal, so that can be utilized to generate clock signal for this microcontroller externally. If you want, you can remove this and you can remove this as well, so that you can use internal oscillator. Okay. Now coming back to the next part, which is going to be V reference. So V reference is going to be this, which is 3 volt that I have added separately. V reference high pin. So you have to have a capacitance as well. So you want, you can use more than 2.2 microfarad capacitor, but I have put 10 microfarad capacitor along with 0.1 microfarad capacitor. So this is the basic, like understanding of microcontroller system that we have done. Now next comes up is the pin mapping for various other functionalities. Okay, so what we have done is we have total 8 pairs of PWMs. You can see PWM 1A, 1B, 2A, 2B, like that, 8A, 8B. Okay, so for 2 BLDC motor driver, okay, what we can do is 3 pair will be required, like up to PWM 1A, say 3A, and 4A to 6A. That is more than enough. Rest 4 are there. If you want, you can use them, otherwise you can discard these and utilize these GPIOs for other applications. Okay. Then we have link communication, we have I2C communication, I2C SDA, I2C SCL, we have CAN communication. Okay, so these 3 interfaces are most popular that you can do. One more thing what you can do is SCI application. Okay, serial communication interface. So SCIA, SCIB, 2 are there, SCIA RX, SCIA TX, something like that. It is actually supporting your UART as well. So UART communication and SCIA communication both will be interchangeable in the same GPIO. We have put one SPI SPI interface as well. So this SPI MOSI, MISO, clock, and STE. So this SPI communication is also available here. Then we have 2 deep switches, 2 push buttons, and 3 LEDs that can be utilized for our normal applications of, like GPIO application, like toggling LEDs or reading the push button data, something like that. Coming back to the analog part, so analog part, what we have is we have DAC output. So 2 pins are used for DAC A, DAC B, and then rest others are used for sensing the voltage level of different kind of sensors. So we have temperature sensor, we have ambient sensor, we have current sensor, 1 current sensor 2 for 2 IPMs. Then we have again like a inbuilt temperature sensor and a humidity sensor in a single IC. We have potentiometer, we have voltage measurement for ADC, VCC, and VDD. VCC is 5 volt, VDD is 3.3 volt. We have 3 current sense pin here, so that like U, V, W phases currents can be taken into account here directly. Okay, after the amplification and everything. We have over temperature like sensing for the IPMs. VOT pin you would have seen. For rugged application, what happens is inside the environment NTC is needed. Okay, so this NTC connector is here, so the temperature NTC can also be monitored. We have fault signal measurement, so fault signal 1, fault signal 2 can be measured from these pins. So hope you have now a good understanding of how you have connected all the peripheral pins that is needed for your IPM system design or motor driver system design, or like any bridge, full bridge rectifier system design and everything. Okay. You want, you can remove some of the pins which is not needed, or you can add various other pins are also available till now, so that you can always do. Let us proceed to the next page. So what we have is we have linear regulator option 2. Okay, so here I don't want to show you right now. First of all, we'll see temperature sensor and humidity sensor. So this temperature sensor, humidity sensor is going to give a VT and VRH, and this is going to go after buffer and filter to our ADC that we just now saw. Then we have NTC, let me make it bigger. Okay. All right, so this is my NTC. So NTC will be connected here at this connector, and this is how a resistance will vary here, RT, and based on that here Vx will be generated. So this V will be, like if you want you can amplify it and then send it to filter and ADC. Otherwise you don't have to amplify, just put a C0 ohm resistor and send it to here. See, voltage level is enough, you don't have to amplify, otherwise you have to amplify. Okay. Similar to that, we have ambient sensor. So this ambient sensor will be used to find out what is the ambient light, or there are some of the applications where ambient lighting is required. Okay. Moving to the next part, we have audio buzzer. So audio buzzer is being driven by one of the PWM that will be driving through this. So this is my PWM that is going to go and drive this particular audio buzzer. So this is a magnetic transducer that will be giving you alarm sound or beep sound, something like that. So you need to have a 50% duty cycle of 2.73 kilohertz PWM. Okay. Then coming back to the EEPROM interface, so we have EEPROM here. Okay. So this EEPROM is 4 kilobits of EEPROM from Microchip technology, and we have I2C interface. You can see I2C L and I2C SCA, I2C SDA. So I2C, their pin net name is I2CA SCL, I2CA SCL. So you can rename this, and I2CA SDA. Okay. Similar to that, we have one onboard temperature sensor, a very simple temperature sensor, which is prominently used in various boards to measure the temperature that is occurring. Because this is a motor driver circuit, so there may be a possibility of temperature rise, and you have to have proper temperature measurement technology. Okay. So this will be sent to your ADC pin, and this is the variation of this particular IC is 10 millivolt per 1 degree centigrade. Okay. So you have to understand that for each degree centigrade increment, there will be a increase of 10 millivolt output. Okay. Per degree centigrade. Now let us go to voltage measurements. Okay. So this is my voltage measurement circuit. So this is 5 volt voltage measurement. After voltage division, let us say Vx is coming, and then this Vx is going to get buffered and then go to low pass filter, and after that it's going to your ADC. Similar to that, we can measure 3.3 volt as well. So by having a proper voltage division, why voltage division we are doing is we want to bring the voltage down to V reference. So my V reference is how much? V reference of ADC is 3 volt. So you have to make sure that this voltage Vx is less than 3 volt. All right. Similar to that, we have one potentiometer. So this potentiometer is very nice to have, and you can utilize for various applications like how calibration purpose, or understanding how ADC can work based on the voltage variation by varying the knob of this potentiometer. Okay. Let us move to the next part. We have user push button here. So user push button, you can see once you press this, then this will get grounded and my microcontroller will see 0. Okay. So this is going to go low, then it will be thought that push button was pressed. Similar to that, this push button 1 also behave the same way, user PB1 and user PB0. So this is protected with proper debouncing and filtering and everything. So this is pipe filter, it is working like that, so that you don't have debouncing effects. Okay. Coming back to the deep switches. So deep switches, you can see if you want to have a IO configuration 0001 1011, then you can use deep switch 0, deep switch 1 for this purpose, and you press it right side, it will be 1, and you press it left side, it will be 0, because it is pulled down. Okay. You want, you can have various other deep switches also. Like I have used here 2 pairs, two deep switches. You want, you can use 4 or 8 arrays, something like that. Let's come back to the LEDs connection. So LEDs, what I have done is, instead of driving by like a MCU IO, I have driven through a MOSFET. Okay, so this MOSFET will be switched on by my MCU, like microcontroller IOs, GPIOs. So once it goes high, my microcontroller will see, I mean my MOSFET will switch on, and then LED will glow. Similar to that, these two LEDs will also work. Okay, so this was all about my iOS applications. Next is we have CAN and LIN interface. Okay, so CAN interface, CAN TX, CAN RX signal is coming from controller side, that is 3.3 volt label. What I am doing is I am sending it through a like voltage level translator to 5 volt, and this 5 volt signal is going to come to CAN transceiver, and this is how it is going to convert it to my CAN high and CAN low to this particular connector. Okay, so this has been like properly terminated also. So if you want, you can remove that. If termination is not needed, it is properly filtered, and it is having ESD diode protection as well. Okay, and this STB is STB, like CAN STB standby mode is permanently grounded, so that it is working in normal mode always. If you want, you can remove that and connect a IO to make it high, so that it will not work whenever not needed. Let us talk about LIN transceiver. So in LIN transceiver, what is going to happen is, we have LIN RX signal and LIN TX signal that is going to get connected to my LIN transceiver, and it will be converting to LIN bus. So LIN bus is properly protected with a ESD diode and filter capacitor. So this LIN bus signal is available to this particular connector. This particular connector is going to have a DAC output also. So these two DAC outputs are there, and with along with 5 volt application is also there for the external interface. Now last comes up is our like power supply. So let us talk about power supply. So in this power supply, what we have is, you can vary your power supply, connect your power supply here at this particular connector, like high voltage and ground. Otherwise, you can have adapter jack, and this adapter jack will give you V input, and this V after fuse we have V in A. This V in A is going to come up as a input for this switching regulator, and this switching regulator is going to convert this V input A to VCC 2 ampere, like 5 volt 2 ampere output it is going to give us. This is having a reset signal as well. So what happens is, whenever this is working within the range, then this LED will be glowing, and whenever it is not working, then it will go low. So whenever this LED is not glowing, it means your 5 volt is not appearing on the board. Okay, so basically reset will go low, it means MOSFET will not be working, it means it will not be glowing. Okay, similar to that, for my GPIO purpose and microcontroller power supply purpose, we need 3.3 volt. So I have one VCC to 3.3 volt conversion. Okay, that is VCC to VDD. This VDD is taken after a like ferrite bed, so that 3.3 volt going to ferrite bed, and then VDD. So this is also 3.3 volt. There is a voltage monitoring like LED also for 3.3 volt as well. So this orange LED is glowing whenever 3.3 volt is appearing. We have reference voltage generation. So you can see like VCC to 3 volt, that is 5 volt to 3 volt generation for your DAC and ADC. One more option is there for power supply. So what you can do is, you can do this one. So this is the connector, and this is the adapter jack, just like what I did in the option 1. And then instead of using switching regulator, we have used linear regulator. So linear regulator V is going to come here and getting converted to 5 volt 0.5 ampere. Okay, if you don't need high current, then this is more than enough. Okay, and similar to that, we have a linear regulator for VCC to 3.3 volt. So this is the way you are going to have a solution using 2 linear regulators instead of 1 switching regulator. So hope you have a good understanding of like how to design the circuit, and what are the various things that you should consider. So if you do have any questions in the pin mapping process, or your microcontroller circuit design techniques, or what are the various things that you should take care of while designing the circuit, you can put down your questions in the comment box, and we shall be able to give you answers as soon as possible with proper explanation. Okay, so all right, enjoy your like this particular circuit, and if you do have a requirement of other C2000 series microcontroller, you can take this one as a reference and you can develop your own circuit based on this particular understanding. And the way you have to like manage your pins, left side, right side, top side and bottom side, you can have a proper reference using this, like how you should proceed. If you want, you can like increase the page size as well, so that you can make this symbol little bigger, and all the GPIOs you can put it left side, so it will look only GPIOs left side, analog pin right side, power supply pin upward, and ground pin downward. Okay, so that is also one more method, but however I like this way, that's the reason like I have put like this. All right guys, thank you.